Hi, everyone, and welcome to Across STEM with YSI, a podcast where we explore how STEM unfolds across countries, cultures, and time. I'm Amirali Banani, your host for today's episode, and I'm so excited to have you join us. Each conversation here is about more than just STEM, it's about stories, ideas, and the people behind them. Today, I'm speaking with Christopher Lee, a neuroscience undergraduate student at Johns Hopkins University, researching experience-dependent synaptic plasticity and neural circuit regulation. Now, I know Chris from Medium. We both are writers on the platform, and a couple years ago when I started writing there, Chris reached out to me to start a publication together called Insights of Nature, with the goal to understand science and the universe better through writing and research. And wow, we had a ton of writers join the publication from all
That's
corners
true.
of the globe. We probably have about 100 or even more articles written and published by them on a wide variety of topics in science. It became quite huge. We have yet to see each other in person, but I'll make sure to visit Chris at Johns Hopkins the next time I'm in Baltimore, or of course, you can come visit me in Seattle whenever. Uh, you know, as two neuroscience geeks, we can visit the Allen Institute together, learn
Mhm.
about some of the incredible research going on there, and talk to some of the crack scientists at the Institute. Hit me up whenever you're planning to come to Seattle, Chris.
Yeah, of course, yeah.
Of course. Now, speaking of research, Chris is involved in some fascinating neuroscience research himself, specializing in patch clamp electrophysiology and is passionate about clarifying the mechanisms regulating neural processing. Some very fascinating things that he will talk about more later in this episode. So, other than that, we will learn more about Chris himself, his background in neuroscience, challenges he's faced, his studies at Johns Hopkins, one of the world's top research universities, his hobbies, and more in this episode of Across STEM with YSI. So let's get into it. Chris, welcome to Across STEM with YSI. It's the first day we're doing this actually, so you're one of the first guests. First
hmm
of all, tell me, how are you doing today? Where are you at right now? What have you been up to lately?
Yeah, I'm so glad to join you here. This is the first time that I'm speaking to Mirali over a call as well. And yeah, so today I find myself in this great place called Dunning Hall here at the Homewood campus of Johns Hopkins University. I actually earlier today just got done doing an experiment that I'm working on for a research project. And it went quite well. It's actually one of the best experiments that I've done in a while. I've sort of get more into that later on around the challenges that you might face in research. But yeah, so today was a pretty good day for me. So I'm quite happy right now. Yeah.
Amazing, incredible. It's the summer, but still on the grind, still doing
On
research.
that grind, on that
On
grind.
the
Yeah,
grind.
absolutely.
Amazing, man. And wow, I mean, from what I've heard, seems like the research you do is truly fascinating. So we'll get
Mhm.
into that more later. Now I want to know, tell us about your background. I, even me, I don't know much yet about you, so I want to get to know you better. Where do
Mhm.
you come from? What got you interested in neuroscience? What was your journey to Johns Hopkins like? Please tell us more about it.
Yeah, of course. So I have always been a lover of science.
Mm.
I feel like many people in maybe our generation would relate to something like this. Like I sort of grew up watching YouTube videos about science, like SciShow, Metaphysics, Veritasium, Vsauce, like that kind of stuff. I've always really loved science, but ever since I was a little kid. Um, I would say that my first interest in neuroscience started when I went to a summer camp through Duke University, actually, where I took a course on, it was called The Brain, Intelligence, and Creativity. And I took this course and I thought it was really, really interesting. And so that course was, as the sort of title suggests, was more in the cognitive domain of neuroscience. But I developed my interest first there. And then when I was in eighth grade, I did a careers project. And I sort of reached out to a local neuroscientist, so to speak, that I knew. And because I'm from a college town, I'm from Tallahassee, Florida. Um, so I reached out to him, and sort of over the years, I ended up doing a research project with him in the summer between my junior and senior year in high school. So that's sort of my rough background before becoming formally trained here at Hopkins. Um, so that's sort of my track. I've really always been interested in science, and neuroscience is particularly interesting to me because I sort of view it as like humanity has developed a certain level of science in all other domains,
Mhm.
and therefore it can now study the brain. Neuroscience it needs it requires that us as humanity like know about a lot of chemistry, a lot of biology, a lot of physics. Like we need to know a lot about other sciences to really tackle neuroscience as a field. And so that was a really attractive property of the field to me when I first started learning about it. And yeah, so I got accepted to Hopkins through the class of 2026. And I joined this lab that I'm working in right now. It's Dr. Alfredo Kirkwood's lab here at Hopkins, and I've been working on here ever since, studying largely the mouse visual cortex for sensory plasticity.
Wow, that is truly incredible. I think especially when it comes to neuroscience, I mean, like me, as a kid, I was interested in engineering.
Hmm.
Part of it comes from like playing Minecraft for like 10 hours a day.
Yeah, 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 yeah.
Um,
That's the stuff. That's the stuff.
right? Uh, Building Lego. I don't know. Like I was just super interested in engineering. I always thought I wanted to do engineering. But then I took this one class, and it wasn't even like about neuroscience. It was a biology class in general. And then one of the units was neuroscience.
Hmm.
And from that one unit, like it just blew my mind. I'm like, wait, this is what I want to do. So
Hmm.
it's just such a fascinating field, even by taking one course or a unit of a course. Like it can just capture your mind so strongly that you just change course. You want to pursue it for the rest of your career, at least. So, wow, that's really interesting to hear. Now, at Johns Hopkins, right now,
Hmm.
how old are you right now? 20.
I actually turned 21 2 days ago.
Oh wow, okay, happy
So
birthday
that was pretty
then.
fun. Yeah, yeah. Thank you so
That's really
much.
cool. All right, so 21 now at Johns Hopkins,
Mhm.
obviously completing your degree in neuroscience, getting your bachelor's, doing research along with it, even during the summer. Um, how does a typical day look like for you at the university? From going to lectures, hanging out with friends, spending time in the lab. What does it look like a typical day?
Yeah, so it sort of depends. So during the summer, I'm largely like a full-time research person here in the lab. So um, because of the paradigm of the experiment that I'm doing, more specifically, I am doing research in circadian uh, plasticity, and so or circadian dependent plasticity, and so it sort of requires me to be in the lab at a certain time, which
Right.
is kind of an interesting wrinkle on the experiment that I'm doing.
Yeah.
So typically, I'm up at like 8 or 9, somewhere in that range, and then I'm in the lab by about 9:30 or so. Which at that time I prepare my dissections, and then I dissect my mouse for the day at like give or take around 10:15 a.m. Sort of the time that the experiment demands. And then I acquired brain slices from that mouse, and then I incubate those slices for a little while. So that's when I sort of eat lunch and I do other stuff that I take care of, and then I do the experiment. So a fun thing about my experiments is that when you acquire these brain slices, they're only good for so long. Like like the cells won't be alive for um, like they're only good for maybe about 5 or 6 hours, give or take.
All right.
So I do the experiment for about 4 to 5 hours, and then I clean up and I go eat dinner. And the rest of my day is just depending on the day. I might play some games uh, on my phone. I might hang out with my girlfriend, or like that kind of stuff. So that's sort of my typical day during the summer. During the semesters, I have to sort of build my research around my class, like lecture schedules. So like for example, last semester, I would come into the lab in the morning. I would start my experiment, and then I would leave in the middle to go to the class, and then come back and then do more do
Wow.
more experiments. So that's sort of how I managed that during the semester. So yeah, it sort of it requires me to build around the restrictions that I have as an undergraduate here. Yeah, but that's sort of how my days look like. And then sort of in the evenings, I'm also part of an a cappella group, so I rehearse with my friends or I do other stuff that I like to do in the afternoon. And of course, I have to study a lot as well. Yeah,
Super busy.
yeah. Absolutely.
And so about that actually, like how do you juggle all this? That's a lot of questions. I think I'm targeting this more towards current high school students who
Hmm.
are going into university. You know, that's one of the main questions they ask. How do you juggle all these classes, research labs? Um,
Hmm.
even like you said, like you go to the lab in between classes sometimes.
Yeah.
What's your strategy here?
So, to the high school students who might be listening to this recording, my biggest advice is to start using Google Calendar or some kind of calendar app,
Yeah,
right?
yeah,
Or some kind of application to help you track what you're going to do for the day. So I feel like when I was in high school, I could largely live on like a day-to-day basis, if that makes sense. Like every day is basically the same. Like you wake up in the morning, you go to school, you done what at like 3 p.m. or something, and then you're done. Like it's a pretty standard like block of time that you just set aside for school, and that's it.
yeah.
But
It's quite
when you're
boring.
in college, no, what's up?
It's quite boring actually. Like high school, just
Yeah.
right, every
It's not very exciting. It's
yeah,
every day, same, same people, same classes, right?
exactly.
Um, and so, but when you go to college, you have a lot more freedom,
Hmm.
for sure. And so, one example that I might give is that, well, if you want to take a certain class, that class will probably have like two or three different time frames to
Yes.
take the class, right? And so organizing your time on like a weekly basis instead of a daily basis is like a really important skill. And of course, as you sort of enter into a more professional field, if you want to schedule meetings with professors, if you want to have, if you want to make like a lab like visit or whatever, or or for myself, if you want to be more serious about doing your experiments, it becomes increasingly more important to plan ahead
Hmm.
um, and think ahead so that things don't like unexpected things don't happen. So in the context of an experiment, I have to experiment with mice that are of a certain age. That's one of the notes about my experiment. And so I have to plan ahead and say, okay, well, this litter of mice will be this age at this time. Therefore, I can do my experiments during that week or something like that. And so, what I would say is start the habit of planning ahead and tracking your time on like at least like a weekly basis. So you have a week ahead constantly about what's coming up, and that'll help you a lot for time management. And that was like the biggest thing that I did when I first went to college as well.
Amazing advice. It's like meal prepping, right?
Yeah,
Spend
exactly,
a couple
exactly,
hours
yeah.
on a Sunday or something, you just make all your meals for a week, and then you're set. Same thing here. Just
Hmm.
spend
Hmm.
a bit of time, make your whole schedule, figure it out, as you said, on a weekly basis, maybe like over the weekends, and then
Hmm.
much more able to actually manage your time in that sense. So,
Yeah, absolutely. Yeah, it's the biggest thing.
very valuable advice, Chris. Now you said you're from Tallahassee, right? Tallahassee, Florida.
That's true. Yeah.
Right. And I mean, it's still East Coast, but it's quite far from Baltimore. How was it
Hmm.
moving away from home? You know, I don't know, it's like a couple thousand kilometers from home. Do you go back regularly to see family? What is it like?
Yeah. So it is quite a distance. It's like a 5 or 6 hour plane ride. Usually with like a little transfer in Atlanta.
Hmm.
That's sort of how my home trips go. I don't visit too often. Maybe like once. Like so, largely you have winter break and you have summer vacation, right? So like 1 month or 3 months. So in the longer breaks, I tend to visit for like a week or so. That's sort of been my routine with that. How was it moving away? It's very different. So Tallahassee is in northern Florida, so it's not quite the blazing Florida that people might think of when they think of something like Miami, for instance. It's not always hot, but it's still Florida, and it's like it's like it's cold for about 2 weeks in the year, and then the rest of it is just hot. The largest thing is probably climate that I experienced moving away. That isn't obviously that isn't like come to university. That's probably the biggest difference that I had. And yeah, it was. I think I adjusted pretty quickly to for that kind of distance. But I definitely know that other friends of mine who are from all over the world um, who had like much harder times adjusting to college. Yeah, yeah.
I see. So in terms of, let's say, because I know um, in the States, obviously,
Mhm.
the culture alone differs a lot between each state. Do you feel
Yes, it
that
does.
difference in Baltimore? Like, do you even feel like you're in the same country or no?
No, no,
Right?
no, no.
It's different.
Yeah, that's the fascinating thing, right? America is really big. Like the United States is like, it's really like 50 countries in a lot of ways.
Yeah.
Like who would imagine that if you take a plane ride from my hometown,
Mm.
which is it's very spacious, if that makes sense. Like it's very widely spread out. Everything is very widely spread out
Like
in
most American
Tallahassee.
cities.
Yeah, yeah. Like you basically need a car to get around in Tallahassee. Um, but if you go to Baltimore, and especially in the sort of the Hopkins bubble, that's kind of what I like to call it. Everything's very close by. Most things are very walkable around here. Um, if you're within the university sort of area,
Mm.
and the culture is also very very different. Tallahassee, Florida, is not that diverse in a lot of ways. Like I think that my high school was like 85% like white, and then it was like 15 like 10% black, and it was like 5% Asian, something like that. It was not very diverse. And also Tallahassee is a very conservative, like there's a conservative region to that town. Like I remember if you were to drive next to the road, like the biggest road next to my house, it's just churches all the way down, like
Mm.
of all the different divisions. It's kind of funny that way. But in Baltimore, things are much more different. Especially Hopkins, the university itself is much more diverse than my hometown. So that's definitely a culture difference that I find. I was like one of two Koreans in my high school.
Mm.
And then, but here, there are a lot of Koreans around here. So that's definitely a good thing for me to have.
Definitely, yes. I was in Hopkins for a summer program a couple years ago.
Yes, I know that.
Yeah, yeah, and it's first of all, I absolutely loved it. The campus, beautiful. I don't know, it's just the vibe it gave was something I didn't experience in any other university campus I'd been to at least. And
Hmm.
I got to live there for 2 weeks, as part of the program, which was amazing. And yeah,
Hmm.
super diverse, amazing facilities, very well connected campus. As you said, you can just walk around easily, get everywhere.
Hmm.
Uh, I think, I mean, it's still one of the places I want to go, maybe for medical school.
Hmm. Oh yeah.
It's always up there on my list.
Hmm.
So
Of course, of
I'd love
course.
to visit
Yes, yes.
again, of course.
Hmm.
Amazing. Now, a lot of people are like, oh my God, neuroscience is so tough, so complex, so much work. How do you handle it? Or are you sure you want to pursue this path? But I say, as long as you're truly passionate about it and are interested
Hmm.
in neuroscience, despite its incredible complexity, you're going to love it no matter how difficult it is to just conceptually understand much of it. Because yes,
That's true.
it's not easy. It's a very tough field, but I mean, as long as you're really passionate about it, as long as you're constantly impressed, constantly beguiled by like everything you read, which is how I
Hmm.
feel. Um, I think it's anyone who's really interested in it should pursue it no matter how hard it is. And I want to ask, like, how do you feel about that? And has there been any points in your academic journey so far where you thought about switching your major, deciding neuroscience is not for you, or have you always loved it so much that you're like neuroscience no matter what?
Hmm. I think I largely fall into the second category of like I really really like neuroscience. I don't think I ever doubted that I would change my major per se, but I have many times thought about changing my like research
Right.
um, field because it's so difficult. So that's sort of what I would say. And one thing about neuroscience that I can I sort of building on what I said before about how neuroscience includes a lot of different fields is that I know. people from all different expertise and areas of study that are neuroscientists.
Hmm.
Um, I might remind the audience, for instance, that it's not actually that long ago where like specific neuroscience programs were developed in universities. Like I have a mentor here at Hopkins who was only a psychology major, because neuroscience majors didn't exist in university when he was a university student, and now neuroscience programs are being developed all around the country.
Yeah.
Um, so I know people who are electrical engineers in training. I know people who are mathematicians in training who are coming to neuroscience because it's such an attractive area to sort of use whatever field you're well trained in, to ask these questions that are really hard to answer. So you might have a biochemistry background or like an electrical engineering background. That I would say there's a lot of ways that you can come into neuroscience, and that's definitely one of the coolest things about it. Um, so I would say that even if you're not specifically like um, crazy about neuroscience like I am, if you just like your particular field of study, but you want to see like an interesting way that your field of study can be applied, then neuroscience is one of the places that you can come to. Because there's so many ways that you can conceptualize things in this field, and that's one of the most interesting things about it. Um, yeah, that's sort of what I'll say about folks who are passionate or not passionate about neuroscience. Yeah.
Absolutely. I think, especially now, the rate at which neuroscience is accelerating in terms of new discoveries, innovations, is insane. It's almost like AI. I mean,
Yeah, 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 yeah.
AI, but you get what I mean. And I mean, AI itself is also helping with that. And in terms of the education too, as you said, it wasn't until recently that like we didn't have neuroscience programs in many schools, and it's still the case. Like when I was applying for universities, uh, particularly in the U.S., a lot of them actually didn't have a neuroscience undergraduate program, at least maybe graduate, but not undergraduate. Um, which is why I had to apply to something else that was pre-med, but I wanted to do
Hmm.
neuroscience, and that's why like at the University of Washington where I am now, it has a very top neuroscience program. But I mean, if I didn't go there for neuroscience, I probably would have gone to somewhere else that would have had um, a good neuroscience program. So
Hmm.
it's really new, um,
It is. Yeah, yeah.
really becoming more and more popular by the day. As you said, a lot of other people in other disciplines are interested in neuroscience. They do research in neuroscience. It's really exciting to see, and I think it's promising considering how much there is we still have to discover in it.
Hmm.
So I hope that more and more people contribute to the field.
Yeah, yeah. And sort of to add on to that AI note that you mentioned AI here, um, like one of the main my knowledge of AI isn't too deep,
Mm,
but one of the most foundational ways that AI has been trained to learn, so to speak, through something called Hebbian learning. Hebbian learning is a posit in neuroscience.
yes,
And so there's a neuroscientific origin to a lot of modern AI models as well. I believe that some folks are trying to like move away from that model to sort of advance the field in a way, but a lot of the work that's being done to develop AI models is based on a neuroscience principle. And so
absolutely, yeah,
there really is no limit to what fields neuroscience can accommodate for people who have an interest. So I might just sort of plug that a little bit on there. Yeah.
exactly. As you said, like Hebbian learning, Hebbian synapses that fire together, wire together.
Mhm.
So much overlap in a sense. Yeah, it's truly fascinating, and this is why I chose to study neuroscience
Yeah,
in the
yeah.
first place. Now, let's fast forward a bit. We call this
Mhm.
segment STEM across time. 50 years into the future, what do you hope we would have figured out in neuroscience? I know there's so much still yet to discover in neuroscience, but if you had to choose one thing in the field you hope we discover, what would it be?
One thing that I hope to discover in that field. That's a great question. Let's see. I would, the first thing that comes to mind is sort of a radically advanced version of what I'm trying to research right now, which is plasticity. Um, so I work in the field of sensory plasticity, and one of the holy grails of this field is that we're trying to figure out ways that we can restore lost senses. So if a patient is either congenitally blind or were blinded after birth, for whatever reason, there must be some kind of way to restore that sense to that person, right? So that's something that I think would be really, really awesome. It's like, okay, well, if this person was either born blind or were blinded later in life through some kind of disease, maybe like diabetic neuropathy or retinopathy or something like that, um, there must be that we can find a way to restore that sense, then that would be like a really big accomplishment of this particular field that I'm
Would be
working in.
huge. Yeah.
Yeah, yeah, yeah. Maybe taking one step further is the general idea of like neural regeneration. So things like spinal cord transections, Alzheimer's disease, like there are just a lot of diseases that or conditions that are caused by the death of neurons in one way or the other. And neurons are, naturally speaking, they're protected by all this bone. Like we have a skull and a vertebrae to protect these neurons because they virtually don't have any like natural regenerating properties like skin. Um, so some kind of breakthrough in that domain will be fascinating to see. And I believe that, 50 years is a quite generous time frame. I think we might get there somewhere in that line. Yeah, I'm hopeful.
Me too. I'm hopeful. I'm an optimist, and I think we can get there, especially with at the rates that I mean, science as a whole is accelerating, and we can, of
Mhm.
course, use AI to our advantage in that sense too. And yeah, I
Mhm.
mean, it just unlocks the cures to so many diseases. Um, as you said, if we can figure out a way to regenerate neurons just as our skin
Mhm.
cells regenerate, I mean, that would be tremendous, honestly.
Yeah, yeah, yeah.
And
Yeah,
yeah,
that'd be great.
totally, totally. And thank you for helping us, you know, progress in that field. You're contributing to it.
I'm
Um,
doing my part. I'm
you're
doing
doing
my
your part.
part. I'm trying.
Yeah, that's what's so incredibly rewarding.
Mhm.
It's just incredible. And my next question is, if you had a crystal ball, let's
Mhm.
say, uh, what discovery or breakthrough would you love to see happen? Um, Now, the previous question, I know you answered this in terms of what you're researching, but this could be anything really.
Mhm.
In neuroscience or related fields, you know, in the next few years, let's say, let's not too far
Next
into the
few
future. What
years.
do you think is feasible? What are we on the brink of discovering?
Mhm.
Um, you can give your thoughts on that from what you've seen,
On
what
the
you've researched.
brink of I would say, well, I'm not sure about uh, the completion of this,
Hmm.
but one of the things that I'm really interested in at least in modern, like contemporary neuroscience, would be something like kinetomics. Um, so for those of you who are unfamiliar, kinetomics is sort of if it's like the human genome project equivalent of neuroscience, basically. So what we're trying to do is we're trying to essentially produce a complete structural map of the human brain down to the synaptic level. And that's as hard as it sounds, way harder than it sounds actually. Um, and we've got a lot of folks working on that. We recently had, I think, relatively recently, we had the completion of the fruit fly
Yes, the micro
brain.
experiments.
Yes, yes, yes. And so it looks like so. I mean, it might be a little bit funny to say, but that's a pretty big accomplishment actually. Drosophila being fully mapped out is a pretty cool thing to think about. Um, and we have the complete connectomics for some other species like C. elegans, for example, where those simple worms that you might see a lot of. We know every single neuron exactly where they come from, down to the developmental pathway of them. Like that's a pretty powerful knowledge to have when it comes to using that species as an experimental subject. And um, so I'm hopeful that maybe in the next couple of years we'll have some more progress in the kinetomics area. And it will be interesting to see. I just like my personal, I just like the idea
Yeah.
of kinetomics and having that map of the brain together. Obviously, it'll have its limitations even if it's fully developed. But I'm hopeful that in the next several years we'll have some good advancements in that domain. Yeah,
Yes, that would be tremendous. Of the whole human brain, I mean, wow, that would be
that's a big deal.
that would be ideal.
That's a
Yeah,
big deal.
like moving on to
Yeah,
the
yeah,
next
yeah.
level in a game, you know.
Yeah, 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 yeah.
Um, and so, kind of like a an extension of that question in a way, um, but more in terms of the discovery aspect. What big question do you think
Mhm.
we still need to solve in neuroscience, or what is the biggest one you think we need to solve? You know, it could be something about consciousness or anything in neuroscience, really.
Mhm.
What do you think is the biggest one, the most important, maybe, that would just, kind of take us to the next dimension uh,
Mhm.
in neuroscience?
I would say the biggest well, hmm, I will borrow the authority of Eric Kendall here, Dr. Eric Kendall, to say that well, the one of the most important things about modern neuroscience is that it is essentially attempting to develop a biology of the mind, right? It's
Hmm.
like we want to have a biological basis for the things that humans do.
Yeah.
Um, for a long period of human history, that has been the domain of philosophers and psychologists, right? Psychologists and philosophers, they're the ones who are sort of in the domain of, oh, humans do certain things and we want to explain why they do those things, right? Or like how they do those things. And that's sort of been their domain. And science, one of the hard sciences, things like physics and chemistry, they were not really involved in that kind of world. But through neuroscience, that now the chemists and physicists are fully involved
Hmm.
in trying to explain the human phenomenon. Um, and so what I sort of conceptualize as the biggest question that neuroscience wants to solve is that at this point in the field we have a pretty large amount of understanding about at the cellular level of things. Like we've done a lot of cellular experiments at the lowest level of the human brain. We know a lot of stuff like what's going on, right? Action potentials, G protein couple of receptors, like that kind of stuff. We have a lot of understanding about that, and then we have like many millennia of psychological experimentation of how humans think, react, and even things like cognitive psychology, come to things like language, memory, and that kind of stuff. Um, we have a lot of understanding on two sides essentially of the scale. Question is what's in the middle, right?
Yeah.
So how is it that these neurons, who ostensibly just fire action potentials and are connected to each other, give rise to things like language and memory, right? So we're trying to bridge that gap. And the gap in the middle, that's the fascinating thing that we're trying to answer, right? So currently, there are a lot of ideas going around in the field of neuroscience. So one of the most popular ones is something like circuit level explanation. So what I mean by that is we want to study the brain not at the individual cell level, but at the level of circuits. So several neurons connected to each other may give rise to properties, well, not may, they do give rise to properties that you cannot observe at the single neuron level, right? So we're trying to bridge that gap from the cells that fire active potentials to human cognition and even to like consciousness, right? So that's the big question that neuroscience wants to answer. So think, in physics you have things like string theory and quantum mechanics and all that kind of stuff, right? All that kind of stuff. Um, for neuroscience, that's the big deal. It's like, how do we get from here to here? Um, answering that question is sort of like the task of the field, essentially. Yeah.
Exactly, because it all kind of feels random. Like you have all these neurons. How the hell does that lead to everything we know? Like, knowledge, uh, storing memories, language,
Hmm.
emotions. You know,
Hmm.
how does all this arise from just these little these little cells in a pretty much just flesh inside your skull? Like, how does it
Exactly.
work, right?
Right, right. But you start from a single neuron,
Yeah.
and you sort of somehow end up with the works of Dostoevsky, or like
Yeah, right?
the pains of Picasso. It's like, oh, like really? So like these cells, and well, at least in the scientific explanation of things, we would say these cells somehow come together in the right exact way to produce the literature of Dostoevsky. It's like,
Yeah.
wow, like how is that possible? And so that's the kind of fun stuff that the field wants to answer,
Yeah.
um, and however long that takes.
It's
Yeah,
truly mind blowing. Just, from electrochemical signals,
right, exactly.
how do you get everything we have?
Mhm.
That's it continues to blow my mind every day.
Yeah, yeah, yeah.
Um, so let's go deeper into your research. We have maybe not too much left, maybe 20 minutes.
Yeah, yeah.
Just tell us more about your research in patch clamp electrophysiology. What does it entail,
Mhm.
and how did you become involved in it in the first place?
Yeah, so for a quick introduction, so patch clamp electrophysiology is a technique that was developed in the 1970s and the 80s. The two scientists who developed the procedure, Sackman and Naher, were awarded the Nobel Prize for the development of the process. And so, essentially, what it is reusing the property of glass. So, glass, especially when it's clean glass, tends to be very sticky, which is an interesting thing to think about glass being sticky. Um, so, what they discover is that glass can really effectively fuse with the cell membrane. So cells across all species of life forms have this thing called the phospholipid bilayer. They have a layer of fat that surrounds its internal side of things. And so the glass can really easily attach to that membrane. And so they discovered that you can actually uh, break that membrane open through the glass tube, and then you have access to that cell in a lot of different ways. This is the foundation of path-clamp electrophysiology. And so our so my work is something we call whole cell patch clamp electrophysiology, which means that I essentially am recording the electrical impulses entering a single neuron through a glass electrode, and that's sort of that is a one sentence summary of what I do basically. Um, Everything else is like additional to that central paradigm of experimentation. Um, I so that's sort of the rundown of that particular terminology. How I'm applying it is in the context of circadian plasticity, as I mentioned before. And so the brain changes. This is like one of the most fundamental things when we think about the of neuroscience, or especially in plasticity, is that the brain can change itself,
Yeah.
right? The most explicit example would be memory. It's like, okay, if you store a memory, there must be some kind of biological substrate that allows that memory to be stored in the brain, right? It can't just be, a whiff of air.
Yeah.
There has to be some kind of reason or like physical manifestation of that memory somewhere in the brain. That has to be the case. Um, so the work that I'm doing is sort of building on the work that the Kirkwood Lab here has been doing for a while now, which is looking at how the brain changes just depending on the time of day. So the circadian clock is the biological clock that we all have in our bodies. And the question that we're trying to answer is, okay, if you look at a sensory area, so specifically for us, the visual cortex, what about the visual cortex changes depending on the time of day? Um, so that's sort of what I've been working on for the last 4 years. So that's sort of the summary of the research that I'm doing. I'm looking at a variety of different things when it comes to that visual cortex and how it alters itself depending on what time of day it is in a circadian context, right? Um, how I got involved in this research is, so this is kind of a funny story that I have. So I essentially emailed the current PI of my lab, Dr. Kirkwood, and I sort of got the confirmation that okay, you can visit at this time. So I showed up at his lab, and I said, my name is Chris. I did research. I saw a bit of a connection to the previous point that I made was that I did research in high school
Mhm.
with the local neuroscientist that I knew. His name is Dr. Sanjay Kumar. He's a great mentor of mine. Um, and I said, hey, like, I did this kind of work in the Kumar lab, and I would love to do electrophysiology work here at the Kirkwood lab. So I didn't know a lot at the time. Like when you're a freshman in college, you're pretty like compared to what I know now, I knew basically nothing. But I said I'm really interested in this stuff, and so I got the opportunity to learn patch clamping at his lab in his lab. Um, it's really hard to learn how to do this technique. Um, it took me about a year and a half, I think, like 2 years,
Wow.
to like get like good at it. I would say, and then after I learned how to do the technique, there are additional things that you can do to make an actual experiment. So you might add some drug or some pharmacology into the bath that the brain size is in to see how those drugs change that neuron's behavior. Right. So there's things that you can do once you learn the central technique.
Right.
Um, and so that's sort of the summary of my research path. There are all kinds of applications of patch template physiology. One of the postdocs in Dr. Kirkwood's lab, he does something called dual patching. So what he does is you patch two cells at the same time. So if one wasn't hard enough, you have two. Um, and then you can measure you can stimulate one of the cells, and it can directly measure the connectivity between those two cells because you can see the response in the other one. Right?
Mhm.
So there's like a whole thing that you can do with this technique, and it's really awesome. And that's sort of what I've been doing for research. Yeah,
Amazing. Really, wow. It took you 1.5, 2 years just to learn the technique.
yeah,
That's
it did.
how hard it is.
It's really hard. Even now, like I'm still learning. The patching itself I'm quite comfortable with now,
Mhm.
at least in the area of the brain that I'm working in. But there are lots of other things that I still need to work on, even though I've been doing it for 3 years now, 3 or 4 years now. So it's a continuous process
You just
of
keep
getting
getting
better at
better
it.
at it.
Yeah, yeah, yeah.
Super. And as part of this research, what are some of the most exciting aspects? And at the same time, what are some of the challenges you faced? The toughest part of it's really.
So the toughest part of it, I would say, I thought a lot about this because I've actually been having a lot of challenges recently with my research. So this comes at a good timing.
Mhm.
Um, the toughest part, and this is what I would say to all aspiring scientists, is that as a scientist, you are trying to, um, in a way, trying to convince Mother Nature to give you some answers, right? You
Yeah.
can't force it out of her hands. You have to do the right experiment, ask the right questions, and do it properly. And then you might, she'll be like, okay, I'll give you this answer, right?
Yeah.
You have to convince Mother Nature to give you some answers, and that's the hardest thing. So what I mean by that in a practical sense is um, like my experiment essentially means that I need to dissect a mouse brain,
Mhm.
cut it into slices, and then record from those neurons. Like that's like it's like inherently that's very difficult. Um, and so basically, what I mean in the context of my experiment is that the cells can die
Yes.
really easily. Like they can die all the time, and it's very challenging to acquire good brain size so that you can actually do experiments on.
Mhm.
Right. So that's a really challenging thing because like it's nature. It's like oh like the brain doesn't like to be cut open. Like oh surprise surprise, right?
Obviously.
Um, and so like that kind of stuff is like that's really challenging. And so in other research areas, if you're doing like more microbiology stuff, your samples may get contaminated. For instance, if you're in chemistry, like your experiment might take 8 hours to run or something. Like there's lots of different challenges, and it's just because nature is in the way, basically. And that is a fundamental challenge of science is that you're trying to convince this Mother Nature to give you some answers, and you have to do it the right way, otherwise it'll just give you nothing. Um, and that's what that I describe the challenge. The most exciting part, of course, is when you do get the answer,
Yes.
right? I was recently told that my data that I collected from my experiments might be included in a publication that the lab is going to produce. And so my data is going to be published sooner or later. And
Amazing.
that's a really exciting thing, right? It's like, oh, okay, like not only did I do this project, but I did it in a way that um, others in my field, especially because as an undergrad, like people that I look up to basically, because essentially the whole field is above me at the current time,
Yeah.
at this point in time. I look up to them, and they will accept my experimental results. So that's certainly the most exciting thing, is that you contribute to the basis of knowledge that humanity has. And so one little thing that my mentor here, his name is Dr. Stuart Hendry, a great mentor of mine here at Hopkins, he told me about the experience of knowing that you are the only person in the history of humanity that knows a certain piece of information. It's like once you have done your experiment and you have your results and you do your analysis and you see the outcome of the results, like at that moment in time, you are the only person in all of human history to know that information. Um, until you go share with everybody else,
Yeah. No, but
right?
wow,
So
what a
that's
way
like
to put it, you know?
right.
Yeah.
Yeah, I like this guy. Yeah, so those are the most exciting things. The challenge is acquiring the knowledge, but of course you know, conversely, the most exciting part is also getting the knowledge, right?
Absolutely. Yes, absolutely. And yeah, you really changed my perspective in a way, saying that nature's in the way.
Mhm.
Yeah, it's like an interesting way to see it. Um, as you said, like, I mean, brains weren't designed to be sliced. Even
Nope.
just cutting it up itself, like knowing exactly where to cut. After all, it's delicate, right?
Hmm.
Know exactly where to cut to get the information that you need,
Hmm.
what nerves you need to look at. It's like there's so many obstacles in the way.
Hmm.
So super complex. Yeah, but yeah, when you get the results, and especially when those results are published, what makes a difference,
Hmm.
it's so incredibly rewarding.
Yeah, it's really rewarding.
Yeah.
Because the work it takes, like any, if you open any biology textbook, right, and you see some figures and some words right on that page, those are hard won. Like
Yeah.
every diagram you see in that biology textbook is like at least a decade of research, at least, if not more. So science is very hard. It takes a lot of work. But I mean, you do something that no other field does. Um, so it's just, yeah, it's just an awesome thing. Yeah.
And not everyone even has access to that research, right? I mean, you have this opportunity to work with these tools, work with these, the specimen. Like, not everyone has access to that. It makes you feel so privileged,
Yeah,
especially
you
when
do.
something, like whether it's a discovery or even just, provide a glimpse into something that leads to a discovery. It's what makes all the difference. It's incredible. So my last question when it comes to your research is, I mean, obviously you did research in high school even, now you're doing it at Hopkins, super top research university, you're doing some world-class research. With all this experience, and you're only 21, but with all this experience so far, what advice would you give to someone who wants to pursue neuroscience, uh, or more specifically, when you're researching patch clap, electrophysiology, or any scientific field in university? Like, what advice would you give? Also, in terms of research, how to pursue research, how to get research positions.
Mhm.
Once you're in research, what to do, and how to develop experience. Just any advice you have, blurt it out.
I would say, especially in the university context, like you are constantly surrounded by people who know more than you. Like as an undergrad in this lab, like I am perpetually around people who know vastly more knowledge than I do. Um,
And that's
so
beautiful.
right, you know what I mean? Like so, for example, I have the lab that I work in, Dr. Kirkwood's lab, that has two PIs. So there's Dr. Alfred Kirkwood and there's Dr. Haeyang Lee, and they're top scientists in this field of plasticity that I am in. Um, they were scientists before I was born. Like, you know what I mean? Like,
Yeah, yeah, yeah.
um, and then there are the researchers, the research faculty here. There's the graduate students. that are here, like I am always surrounded by people who know more than I do. Um, and like once this is also a great experience for me when I first came to university is that especially the professors like they know like a lot, like really a
More than
lot.
you think, yes.
Yeah, yeah. Like you like it's like you can't even conceptualize how much more they know than you do. Like as a and I had a story from a specific interaction that I had, but maybe that's for a later time. Um, but if you go into research, like ask questions to those people, like
Yes,
just run around and like just
as aggressive as
ask
you can.
questions.
Yeah.
Just be curious and like just ask questions. And generally speaking, the people in the academia field are very happy to answer your questions. Some of them are like, they're they're just bursting to answer questions.
Yeah,
Like
yeah,
myself,
yeah.
sometimes I'm also of that variety where I'm just like, I really want to ask questions all the time.
And
And
they like
so
it.
ask,
They like it.
and yeah, ask questions to people, and because they know so much more than you do, you
Hmm.
will get answers and solutions that you cannot even imagine. Like so, um, for example, like I was stuck on this experiment that I was working on. I was getting this observation that I just did not know what to make of it. I'm like, I don't know what this is. This makes no sense. Like, because of my knowledge of neuroscience at that time, could not explain this thing that I was observing
Hmm.
in this experiment. So I went along to my PI and I'm like, hey, Dr. Lee, like, do you know about this thing? And she's like, yeah. This because of like in like 5 seconds gives me an answer. And that's like in some sense that's quite obvious. Like, of course, like she knows this answer and I don't.
Hmm.
Um, but if I hadn't asked the question, and if I hadn't sought out the answer from the people around me who know more than I do, then I would not know that today, because there's no way to like synthesize the knowledge. There was no way to just based on the knowledge that I had acquire the answer to that question. I had to go to someone else.
Absolutely.
Um, so if you're in university, and if you're in the research lab, and once you're doing your research project, the couple of stages involved there, always ask questions to the people around you because they know more than you do, and that's such a valuable thing to have. Um, like
Definitely.
literally any lab member, just like ask a question, and you will probably get an answer that you will learn from, and that's a really fascinating thing.
It is actually um, one of my relatives. They said an analogy that stuck with me back
Mhm.
when I was in high school. They said, especially when you go to university, be like a sponge for information. You know,
Yeah.
from any source you can, professors, PIs, TAs, just absorb their information, ask anything, even when you think you know the answer, ask. Just stay curious all the time because they're often the best source of information, not just the most immediate, but also the best source of information uh, who you can learn from, really. So, you know, while you're in university, right, which is not a very long amount of time,
Mhm.
use what you have, the resources you have, absorb their knowledge in a sense. Be a
Yeah.
sponge for knowledge, for information.
Mhm.
It'll go a long way.
Absolutely.
Now, moving into our final segment, this is a special one,
Mhm.
specifically about growing up in the US
Mhm.
and your experience in STEM growing up in the US. So,
Mhm.
do you have a cool or surprising STEM fact from the United States? Something most people wouldn't know? I mean, like you, I also study in the US, but we're on completely opposite sides of the country. As we said,
Mhm.
it's like, as you said, it's like 50 different countries, and there's a
Yeah,
lot
yeah.
that differs culturally, even scientifically. So, but what do you think is one American STEM fact that you think is unique to
Man,
America?
an American STEM fact.
Yeah. Could be in neuroscience or anything else.
Let's see.
Even something from Johns Hopkins.
What would I say? I guess my immediate answer that I want to give is that NIH funding has supported the vast majority of pharmaceutical drugs in this country. Um, I recognize that that's like I think it's like in the 90 percentile, like something in that range.
Wow.
Um, the correct figure, the exact figure eludes me, but it's like the vast majority of drugs that America and the pharmaceutical companies have developed originate one way or another through NIH funding. So I recognize that that's a pretty contentious note to give, maybe in the current climate around science here in America.
Mhm.
But it's true. So that's sort of my America stand fact, I guess. Yeah.
Absolutely. And that's something I didn't know, but yeah, it just speaks to how critical funding is. And unfortunately, like now with, of course, the Trump administration, I don't want to get into politics, but it's sad to see how much the funding cuts are actually affecting research because it truly
Mhm.
makes a difference. NIH makes a huge difference. And to see that funding cut is like, you know, it's like cutting a source that is vital to not just research in the US, but global research because there's so much research that goes on in the US that really affects the whole world. So I hope this is something that, you know, won't last too long.
Mhm.
But yeah, it's incredible how much, like the NIH contributes.
Yeah. Like so what I will say is that there's a constant like debate over prioritizing translational versus basic research,
Right.
right? Or applied research versus basic research, right? And but what I want to say on that note is that um, applied research essentially uses basic research as its fuel, right? If if you don't fund basic research or you don't support the field, I guess, doesn't support basic research, then eventually the applied folks will run out of knowledge to
Exactly.
use.
Exactly.
Um, this well, like, we just don't know how this
Yeah.
region in the brain works, or we just don't know how the circuitry works, and we need some basic scientist to go in
Mhm.
and answer the question about how that brain region works. And then after that, we can start thinking about treatments or drugs or other experiments, right? And so I think that, uh, Hopkins, perhaps more than many other schools, is really involved in that kind of research. We have one of the best medical schools in the world here, and the research that goes on at the Johns Hopkins School of Medicine uh, is like it's peerless. That's my personal opinion. I'm sure that there are other. That's a hot take,
Yeah.
but
No,
that's a
no.
little bit of school pride on there. But yeah, I mean, we have fantastic research here. Um, and it's just an important thing to know of how science develops is that there are people who do basic research, which might not always get, the shining awards or the new fancy drug that comes out in the market.
Mhm.
But you have to just have that certain level of knowledge, otherwise that applied research is impossible.
Absolutely.
Um, so that's what I would say about, I guess, American scientific research is that we've done a lot of basic research here. And that's been a pivotal part of advancing science for humanity as a whole.
Definitely. Yeah. Otherwise, I mean, it's like the foundations. You need the basic research. Otherwise, it's like cutting the columns of a building, chopping it off,
Yeah. Hmm.
right? Um, so that foundation, the basic research always has to stay strong so that the higher levels like applied research can progress.
Hmm.
Well, Chris, thank you so
Yeah.
much. That brings us to the end of this episode of Across STEM with YSI. Um, a huge thank you to you. I mean, I know you're busy. You're doing so much research over the summer in the lab.
Hmm.
You just came from the lab. But regardless, thank you so much for joining me and sharing such thoughtful insights on your amazing career so far in neuroscience and all that you're
Hmm.
contributing. To the audience, if you enjoyed this episode, please make sure to follow the podcast and check us out on socials to stay updated. We've got some more incredible guests and conversations coming your way. Until next time, stay curious, stay inspired, and keep exploring STEM across borders and time. Chris, thank you so much.
Thank you.